Welcome back to another explainer. All right, today we are taking on Domain C of the test content outline, and we're diving into a foundational concept that, well, frankly, candidates stumble over it all the time. Look, if you're gearing up for your exam, getting a rock-solid grip on measurement metrics isn't just some box you check off. It's literally the absolute foundation of everything you're going to do in practice. We're going to break down the real concept of measurement accuracy, look at the science behind it, and, most importantly, we're going to show you exactly how to escape this ultimate trap that catches so many test takers completely off guard.
Okay, let's dive into this, because the quote we've got right here, it perfectly sets the tone for exactly what we're dealing with. The exam creators will punish you if you don't know the exact mathematical line that separates them. I mean, wow, that is a sharp, undeniable reality right there. When you sit down for that exam, they're not tossing you soft, high-level overview questions. No way. They are testing your absolute precision. They want to know if you actually understand the strict scientific boundaries between concepts that, honestly, sound pretty much identical to the untrained ear. The stakes are incredibly high, and nailing down these precise boundaries is exactly what we're tackling today.
Accuracy, reliability, and validity. Now, in just everyday casual conversation, people use these words almost interchangeably, right? Someone might say a test is accurate when what they really mean is it's valid, or they'll say their data is reliable when they're actually trying to describe its accuracy. But listen, in the rigorous world of behavior analysis and measurement science, treating these terms as synonyms is a fatal error. It really is. That casual interchangeability is the main obstacle we're breaking down today. You've got to learn to just completely separate them in your mind.
So to get past that obstacle, we actually need to put reliability and validity to the side for just a second. We're going to isolate our core concept in a total vacuum and focus entirely on defining true accuracy.
Let's look at the official definition here, pulled directly from our source, glossary1.pdf. Accuracy refers to the extent to which observed values, so the data produced by measuring an event, match the true state or true values of the event as it exists in nature. I want you to really listen to the heavy scientific weight of that phrase, match the true state. This isn't about how nice your data looks on the spreadsheet or how neatly you collected it. It's asking a very strict question. Does your observed value reflect the undeniable reality of what literally just happened in nature?
And this brilliantly illustrates the concept, the classic bullseye analogy. Think of the true value of an event in nature as the absolute dead center of a target. Accuracy is simply a measure of how perfectly your recorded data point lands on that exact center, right? If the true value in nature is the bullseye, any deviation from that center, no matter how tiny, means a loss of accuracy. Your observed value, the dart you're throwing, has to hit the absolute center of the true state to be considered perfectly accurate.
But here is where we hit the trap. Let's pivot sharply and talk about the false friend here, reliability. If accuracy is hitting the bullseye, reliability is the imposter. It's the thing that makes you think you're doing a fantastic job even when you are missing the mark completely. And guys, this is the ultimate trap for test takers. Reliability feels so much like accuracy when you're in the trenches collecting data. It gives you this total false sense of security. And guess what? The exam creators know exactly how to exploit that confusion to trip you up. To avoid that trap, we have to define reliability very strictly. Reliability is simply about replication, period. It's getting the exact same reading over and over again. That's the whole shebang. It's a purely mechanical process of repetition. Now, the absolutely crucial thing you need to remember right now is that mechanical replication does not guarantee truth. You could do the exact same thing 10 times in a row perfectly, yielding flawlessly reliable data, and still be completely divorced from the true state of the event as it exists in nature.
Let's contrast these two concepts side by side to really lock in this mental model. Imagine a broken bathroom scale. You step on it 5 times in a row, and it reads exactly 150 pounds every single time. Now that scale is incredibly reliable, right? The replication is flawless, but it's fundamentally broken, so it's completely inaccurate. Now contrast that with a properly calibrated scale. When you step on this one, it hits your true weight perfectly. It matches the true state of nature. You really need to keep this visual of the broken versus calibrated scale in your head whenever you're evaluating measurement metrics. It's a total game changer.
Now, what's really interesting about this scenario is how we can take this mathematical dichotomy and drop it directly into a real-world clinical data situation. The scale analogy is great for learning the basics, sure, but you're not going to be tested on bathroom scales. You're going to be tested on behavioral observation. So let's step into the shoes of a video observer who's tasked with tracking a specific behavior across multiple sessions. Let's see how reliability and accuracy actually play out in the field.
Imagine an observer who sits down and watches a session video. They meticulously log exactly 10 instances of aggression. Then, they watch the next session, and they log exactly 10 instances again. They do this day after day, session after session, faithfully recording those exact 10 instances. If you're just looking at their data sheet, you might be thrilled. Their data collection is highly reliable. They are achieving perfect replication. From a purely administrative standpoint, it looks like incredibly solid, dependable work.
But here is the shocking revelation. What if the client actually aggressed 25 times in nature? We finally uncover the true value of the event, and it's 25. Our observer, who was so incredibly consistent and so wonderfully reliable, entirely missed 15 distinct instances of the behavior. I mean, think about the massive gap between the 10 instances they recorded and the 25 instances that actually occurred. The true state of the event as it existed in reality was completely missed by our perfectly consistent observer.
So the crucial point is this. Because that observer missed those 15 instances, their highly reliable measurement possesses absolutely zero accuracy. Just let that sink in for a second. Zero accuracy. Their data is reliable, yes, for sure, because they did the same flawed thing over and over again. But it doesn't match the true value in nature. And this is exactly how the exam is going to try to trick you. They'll present a scenario with beautifully consistent, replicating data, and they'll tempt you into assuming it's accurate. But as you can clearly see, reliable data simply does not equal accurate data.
Which brings us to the ultimate question you must ask yourself every single time you analyze a dataset. Your measurement data is perfectly reliable, the trends are consistent, the replication is flawless, but is it actually true? Does it match the event exactly as it exists in nature? I really challenge you to carry that provocative thought with you. Always question the underlying truth of your data before you just blindly trust a perfectly replicating trend. Because in the end, if your data isn't true, well, everything built on top of it is just a reliable illusion. Thank you so much for joining me for this explainer, and I will catch you in the next one.